Welcome to today's lecture on lesson L26, inverse differential operators and partial fractions. We'll begin by reviewing partial fractions for polynomials, for rational functions, and then we'll discuss how partial fractions are used to compute inverse differential operators. So here's an example. I think partial fractions are best seen via an example. Let q of x be this polynomial x squared minus 1 times x plus 1 squared times x minus 2. Notice it's factored into these factors here. Let p of x be any polynomial of degree less than q of x. Then p of x over q of x can be rewritten as follows. P of x over q of x equals ax plus b over, sorry, that should have been an x squared minus 1 plus c over x plus 1 plus j over x plus 1 squared plus h over x plus 1 plus j over x minus 2. What's important here is that, as you can see, the numerator always has degree 1 less than the term that's either in the denominator or the factor that's in the parentheses in the denominator. So here, what's in the denominator, first term, what's in the denominator is x squared plus 1. What's in the numerator is ax plus b. That polynomial in the numerator has degree 1. Polynomial in the denominator has degree 2. Second term, polynomial in the denominator has degree 1. Polynomial in the numerator has degree 0. And likewise with all these other terms. Now here, x plus 1 squared, notice we have two terms with denominator that includes an x plus 1 factor. That's because x plus 1 appeared twice when the polynomial was factored. So we have to also include it twice when we make the expansion with partial fractions. C over x plus 1 plus j over x plus 1 squared. Numerator, though, stays the same degree 0 because what's in the parentheses has degree 1. 1 minus 1 is equal to 0. And you don't need to worry about this term. There's just these, it should have just been 4 terms. Okay. The numerator always has degree 1 less than the factor in the parentheses in the denominator, as we said. Now let's go over an example. Let's consider this function, this fraction, 1 over x cubed plus 3x, which is the same. When you factor out, so this should have been an x squared. So 1 over x cubed plus 3x is 1 over x squared times x plus 3. That's the same as 1 over x squared times x plus 3. We can rewrite this as a over x plus b over x squared. Notice x isn't in the parentheses, but if it was x plus a constant, it would be in the parentheses. So you want to think of x, the denominator, as being in the parentheses. Here it's a over x plus b over x squared plus c over x plus 3. 3 terms. These two correspond to the double factor of x in the polynomial in the denominator, and this x plus 3 factor is the second factor. And notice no factor here. X appeared twice, but it has degree 1. X plus 3 appeared once, it has degree 1. There is no factor in the denominator that had degree 2 or larger. If it did, then we would have included an ax plus b, or ax squared plus bx plus c. That is a polynomial in the numerator that had degree larger than 0. A, b, and c, if you add all these up with a common denominator of x squared plus x plus 3, what do you get? A times x plus 3. So this is just multiplying a times x to get to x squared, and then times x plus 3 to get to x squared plus x plus 3, plus b times x plus 3 to get to x plus 3 times x squared is x squared plus x plus 3, plus c times x squared. Multiplying x plus 3 times x squared gives you x squared times x plus 3. So these three terms have to add up to 1. If you distribute and collect like terms, you get a plus c. So it's a plus c because a times x is x squared, a times x squared, c times x squared, you factor out a plus c, you're left with a plus c times x squared, plus 3a, that ax times 3 is 3a times x, plus b times x, just b times x, so we can factor out next from those two terms, 3a plus b times x, plus 3b, that's just from distributing the b to the 3 over here, and these three terms have to add up to 3. I'm sorry, to 1. Not 3, that was an error. To find a, b, and c, we solve the following system. 3b is 1, 3a plus b is 0, a plus c is 0. Solving 1 gives you b is equal to 1/3. Plugging b is equal to 1/3 into 2 gives a is negative 1/9, right? Because b is 1/3, a is negative 1/9. Plugging a is negative 1/9 into 3. So we just plug in this into here. C is its negation is negative 1/9 is positive 1/9. What's our conclusion? 1 over x cubed plus 3x squared is negative 1/9 over x plus 1/3 over x squared plus 1/9 over x plus 3. Partial fractions and inverse differential operators. P of d is a linear differential operator. That means a polynomial operator. P of d inverse is 1 over P of d. This can be written using the method of partial fractions, the same method procedure that we used for fractions. In particular, here's an example. D cubed plus 3, again, this should have been d squared, is the same as 1 over d squared plus times d plus 3, which is the same as negative 1/9 over d plus 1 over 3d squared plus 1 over 9 d plus 3. These are the same terms we obtained from the partial fraction expansion of x squared times x plus 3. So it's the same thing, just x here is replaced with d, the differential operator. So here's an example. Let's use inverse differential operators to find a particular solution. Here's a problem. Solve y triple prime plus 3y double prime is 5x squared. We're going to rewrite this using the differential operator as follows. P of d times y is 3x squared, where P of d, again, this should have been 3d squared. So d squared factors out, d squared times d plus 3. And we found that P of d inverse is equal to 1 over P of d, which is equal to 1 over d squared times d plus 3, which is negative 1 over 9 times d, plus 1 over 3 times d squared, plus 1 over 9 times d plus 3. When you apply this to 3x squared, you get negative, you just apply each of these operators to 3x squared. Negative 1 over 9d applied to 3x squared, 1/3 over d squared times 3x squared, 1 over 9 times d plus 3 times applied to 3x squared. And times is the same as applies to. Now, these two terms are pretty simple to evaluate because 1 over d and 1 over d squared, that just means anti-differentiate once or anti-differentiate twice. That is, integrate once or integrate twice. This, however, is going to be just a little more involved. We did have a formula for it in last lecture, and that's what we're going to compute right now. So if you recall, 1 over d plus 3 is the same as 1 over d minus negative 3. We had a formula for 1 over d minus a, and it's equal to 1 over 3 times 1 minus 1/3 d plus 1/9 d squared. So the formula was 1 over d minus a is equal to negative 1 over a times 1 plus d over a plus d squared over a squared plus blah, 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 blah. So here our a is negative 3. That's why this is a negative 1/3 and this is a positive 1/9. When you apply it to 3x squared, go through that calculation. You can check this over on your own. But what you end up with is 1/9 x squared minus 2 27th x plus 2 over 80. And as we said here, this is just negative 1/9 over d applied to 3x squared. That's just the same as anti-differentiating. The antiderivative of 3x squared is x cubed. We're left with negative x cubed over 9. The antiderivative of 3x squared, we apply it twice, x cubed, so it's x to the 4th over 4, so it's 1/3 x to the 4th over 4. That's x to the 4th over 12. Here's what we found. Example continued, putting all the terms together. Negative 1 over 9d applied to 3x squared, it's negative x cubed over 9. 1/3 over d squared applied to 3x squared, it's x to the 4th over 12. Add 1 over 9, d plus 3 applied to 3x squared, it's 1/9 x squared minus 2 over 27x plus 2 over 81. Now, here's an important thing that we didn't really have to worry about when we did the other method of just applying 1 over d plus 3 first and then 1 over d squared. These two terms are extraneous because when you plug them in to the differential equation, you just get 0. So they're not going to affect the particular solution. We can actually just drop them. They are actually part of the general solution. So in other words, the polynomial differential operator, d squared, applied to d plus 3 will send these two terms to 0. Now if we add up the rest of the terms, so we're just left with this term, 1 over 9 x squared, the next highest term, which is negative x cubed over 9, and the highest term, which is x to the 4th over 12, x to the 4th over 12 minus x cubed over 9 plus x squared over 9. You can indeed check that this is a particular solution of the differential equation y triple prime plus 3y double prime is equal to 3x squared. You're going to have a homework assignment, a written homework assignment on grade script that's very similar to that, as well as an extra credit problem that is related to that and just involves the formula for 1 over d squared plus d minus 1, or 1 over d squared plus a constant times d plus a constant. That is, the polynomial in the denominator is going to have degree 2, not just 1. There's a formula for that you're going to need to look up in the textbook if you want to do the extra credit. Okay, so that's it for today's lecture. I will see you all on Monday.